Hello everyone, this is a homework problem that I had assigned in class, and I'm also just going to record it so you can have access to it at home. So this is the homework problem. I think it was problem number 2 or 3, I can't remember the number now, but this is the problem I had given you, and I think we can change this to S of t. Let me just erase that. Whoops. So this S of t was this function right here. And just for good practice, it's good to just go ahead and set up the velocity and acceleration function ahead of time, just so that you have it. So here's the position function. When I find the derivative of S of t, I get this. When I find the derivative of the velocity function, I get the acceleration function, which is this. So go ahead and pause this and see when you find the derivative if you end up with the same functions. Okay, moving right along. The second question I ask is so I ask what the velocity is, and it's right here. The second thing I ask is, what is the velocity at 3 seconds? And at 3 seconds, when you plug in 3 into the velocity function, you get 0. So the particle is at rest and it's changing direction, because that's what you know. When the velocity is 0, your particle is either at rest and or changing direction. So the velocity here is 0 feet per second. The next thing I ask is, when is the velocity 0? When is the velocity 0? Well, we already know that the velocity is 0 at 3 seconds. But let's actually go ahead and solve. So we're going to set the velocity. Whoops. Let me undo that. So we're going to go ahead and set the velocity function equal to 0, which I have right here. So I set it equal to 0. And I actually can factor out a 0.04. I mean, it's just like if I had 4 and 12, except I have 0.04 and 1.12. So I can factor out a 0.04 or 4/100ths, and I can also factor out a t squared. And that makes that a lot easier to solve. So when you do that, if I set this equal to 0, I get t equals 0. And if I set t minus 3 equal to 0, if I set this equal to 0, I get t equals 3. And we knew that already. We knew that the velocity was going to be 0 at 3 because we evaluated it at 3 in the previous part of the problem. And let me just make a note here. Oftentimes when we factor, you ask me in class, well, can't we set it equal to 0? If it's a constant, no. If I had just 0.04, for instance, I could not set 0.04 equal to 0 because 0.04 equals 0.04. But because I have, let me just change colors here, because I have a variable here, I can set it equal to 0. So anyway, the velocity is 0 at t equals 0 and at t equals 3. Okay. The next question is, when is the velocity greater than 0? So I figured it's already in factored form. So this is the same thing. This is the velocity function. It's just in factored form here. And when will this be greater than 0? Well, it'll be greater than 0 when t is greater than 0. When t is greater than 3, because take a look. If t is 3, I have it at 0. If t is 2, that's negative. If t is 1, that's negative. In fact, if t is any number less than 3, this whole thing is negative. So 3, any value greater than 3 is going to make that positive. So that's the answer to that one. The next thing you're asked for is the distance. What is the distance that the particle traveled? And remember, the distance is going to be the absolute value of its distance moving forward and the absolute value of the distances or distance moving backwards. And as we discussed in class, the best way to do this really is to go ahead and fill out your chart. Remember, you're going back to the position chart, not the velocity chart. We viewed velocity all along, but if I want to know where this particle is going, that's the position. That's not how fast it's going and in what direction. I just want to know not how fast it's going, but I want to know where it's going. That's the position function. So I evaluate at 0, I had to kind of squeeze in here, but at 0, my particle is at 0. When t is 1, and I plug this into the original position function. So just a reminder, I'm plugging this in here, this function right here. Okay? And go ahead and pause and see if you get the same S of t values that I get, okay? Plugging in it from 0 to 8. Okay, so I have that, and that's going to come in handy when I draw my diagram, but it's also handy when I try to find the distance. Notice here the particle is moving to the left, and here the particle is moving to the right. How do I know it's moving to the left? So it starts at 0, and it just goes farther and farther away from 0. And then at 4, it is 0, and then it starts to go farther and farther to the right. So I know I'm kind of doing this thing. And the distance is going to be the absolute value of this length, or this length plus this length. And I'm going to find length by the absolute value of that. So again, this chart comes in really handy. So my distance is going to be the absolute value of S of 3 minus S of 0, because that's where it's right before it changes direction, and plus S of 8 minus S of 3. So kind of like what we said here. It's going to be this distance plus this distance. So and here I have it here for you. And let's go ahead and see. So the absolute value of negative 0.27 minus 0 plus the absolute value of 24.48 minus a negative 0.27. Watch your signs here. So the distance is going to be 21.02 feet. That's the distance that this particle traveled. Okay, and the next question is to draw the diagram. So this makes this really, this makes this really easy. Let me see if I can actually cut this chart and put it on the bottom. Let's see here. I'm not sure I can do this. Let me try. Let's see. Okay. And I'm going to put this down here. And okay, so I'm not going to waste everyone's time with that. We'll figure that out later. Anyway, so at t is 0, remember let me just change colors here. At t is 0, my particle was at 0. At t is 1, it was at 0.03. At t is 2, it was at negative, so these are all negative values, negative 0.2. At t is 3, it was negative 0.27. And at t is 4, I'm back at 0. So I'm just going to draw arrows. From 0 to 3, I was going in this direction. And at t is 4, now I'm going in the positive direction. At t is 5, I was at 1.25. If you go back to the chart, at t is 6, I think I'm at 0.432. Let's double check. And t is 7, t is 8, t is 9. I think we stop at 8. At 8, I'm at 20.48. So I just keep going in the positive direction. So that's what the diagram looks like. You don't have to put these arrows. I'm just putting them just to let you know what direction the particle is going in. For part G, it says find the acceleration after 3 seconds. Okay, so let's go ahead and do that. Let's see here. So A of 3, A of 3. And you can go ahead, again, you can go ahead and do this and then just pause and see if you and I get the same answer. So A of 3, this ink is too thick, sorry guys, let me see here. There we go. A of 3 is going to be 0.123 squared minus 0.24 times 3. And that equals 0.36 feet per second squared. So positive. So let's see here. 0.36 feet per second squared. So that's the acceleration. Okay. And now we have to find out when is this graph speeding up and when is this graph slowing down. And to do that, we have to set the acceleration function equal to 0. So let me just move this. So first, let's find the critical value for the acceleration function. And when is the acceleration function equal to 0? When will 0 equal, let's see here, let me just find the acceleration function. Point t squared minus 0.24 t. All right, so I can factor out actually. So 0 equals 0.12 t. I can factor that out, and I'm left with t minus 2. And my acceleration is at 0 at, so a of t equals 0. When t is 0, right, set that equal to 0, you get 0. And at t equals 2. Okay. So now let's go ahead and line up my velocity function and my acceleration function. So my velocity function, my critical values were 0 and 3. And for the acceleration function, my critical values were 0 and 2. All right, so let's go back to the velocity function. Let's see, from 0 to 3, if I plug in any value between 0 and 3, and we can go back, we already kind of know the answer, but let's just go back to the velocity function that we solved for. And I'll just use this one because the factored form is much easier to work with. If I plug in a value like 1, I'm going to get negative. Remember, we already solved earlier in the problem that velocity is greater than 0 only when t is greater than 3. So I know that I'm putting minus signs for this first part here. So minus, 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 and then after 3 it's positive. And what about the acceleration? Well, for any value less than 2, you can just tell by looking at it in here. For any value less than 2, I'm going to have negative acceleration. So this is going to be negative, 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 negative. And for any value greater than 2, it's going to be positive. So here are my partitions. So let's see. And I can say that the particle, so now we can answer the question. This is the motion analysis. So particle is speeding up. Let's see, between 0 and 2. So between 0 and 2. And the particle is also speeding up for all t values, for all values of t greater than 3. So when time is greater than 3. Because from 0 to 2, it's negative, negative. So the acceleration and the velocity are going in the same direction. So it's speeding up. And also anything beyond 3, it's positive, positive. And the only time it's slowing down is in between 2 and 3. So I can say, whoops, that the particle is slowing down when t is between 2 and 3. And why is that? Well, because it's the velocity and the acceleration have different signs at that segment, at that portion. And I hope this helps. Okay, bye-bye.